Welcome. In this video, we are going to explore taking antiderivatives of polynomials using the power rule. Why do we want to take antiderivatives? Well, the simple answer is it undoes a derivative. It's the opposite operation of a derivative, kind of like how multiplication and division are opposite operations of one another. In physics, we learned that the area beneath a velocity versus time curve will give us the displacement. Taking the antiderivative is the first step in finding the area between a curve and the horizontal axis. And other times we're going to be taking the antiderivative to find equations of motion. If I give you the acceleration, you can take the antiderivative and do some other things after that to figure out what that equation for the velocity might be. Okay, so let's take a look at the power rule. We have a function here, y is equal to ax to the n. A and n are just numbers, just constants. And remember, from taking the derivative, we take the exponent n, multiply the coefficient a by that, and then n drops by 1, a whole number, right? So we're going to do the opposite of that. So instead of n decreasing by a whole number, n is going to increase by a whole number. And we're going to do that first. So we're going to go x to the n plus 1. All right? And then in the front, instead of multiplying a by the exponent, we're going to divide a by that new exponent. All right? And so here then is the antiderivative of that. And I'm going to introduce this notation. That's integral notation. And we'll see later why it's a big S. It stands for a summation. We're adding up a bunch of tiny little areas here. Okay, now there's one extra added step here. When we do an antiderivative, we have to add in a constant at the end, c. And the reason for that is, I told you, derivatives and antiderivatives are opposite operations of one another. They undo one another, right? So if I took the derivative of this thing, I need to get this thing back again, right? And remember, the derivative of any number, any constant, is 0. So that's not going to show up here when I take the derivative. So I'm acknowledging the fact that there could be some added constant at the end of this antiderivative. And whatever that constant is, when I take the derivative back again, it's going to go away and give me what I wanted. All right? Now that's a little bit confusing, I'll absolutely admit. So let's take a look at an example. All right, so let's say we've got y is equal to 3x to the 4th. Okay, so the steps are kind of reversed from taking the derivative. Remember, derivative, you multiply exponent and coefficient first. Here, we're going to deal with the exponent first, and we're going to raise it by a whole number. So x to the 5th is our new exponent. Then we're going to take the existing coefficient and divide by that new exponent. All right? And we're going to add in our lovely constant. So this is the integral of our function. Antiderivative. Let's not go integral yet. All right? So this is the antiderivative of our function, 3x to the 4th. Okay? And we can always check it by taking the derivative using the power rule. So again, derivative using the power rule, you multiply the exponent times the coefficient out front. 3/5 times 5 over 1, we end up with 3, right? And then the exponent drops by a whole number. We're back to 3x to the 4th, and the constant goes away when we take the derivative. So check. We got our derivative back again. That means we took the antiderivative correctly. And the nice thing about this, you can always check your work. Take the derivative again. After you've taken the antiderivative, you should get the original function back again, right? So can we use the power rule for antiderivatives to take the derivative of a constant? Yes, we can. If we then kind of write it as a polynomial. So 2x to the 0. Now we can kind of apply the power rule here, right? So we're going to say the antiderivative of r, and again, we deal with the exponent first. Raise that by 1, and then you're going to divide the coefficient by the new exponent, 2 to the 1st, which, simplifying this out, is just 2x. Okay, so the antiderivative of a constant is just going to be that constant times whatever variable you're using. All right, so in this case I used an x. And I did forget something. We're going to add in that possible constant that's in there. All right, so yep, you can take the antiderivative of a constant. How about the antiderivative of something a little bit trickier, like x is equal to 3 square root of t? Can we use the power rule for the antiderivative here? Yup. Just like we did with derivatives, we're going to rewrite this so that we can use the power rule. We'll call it t to the 1/2. So now here's my function rewritten. And again, we deal with the exponent first. That goes up by 1. So we've got t to the 3/2 power now. And we divide the coefficient out front by the new exponent. 3 divided by 3/2. So, boy, let's see. I think I'm doing this right. That's going to be 6/3 or 2. T to the 3/2 plus, as always, the ever-present constant of integration. So there's the antiderivative of that function x. Okay, now at this point you might well be asking, well, does the power rule for antiderivatives work for negative exponents? Indeed it does. So this doesn't look like it's going to work for us, but let's rewrite it as 1/3 t to the -4th. Okay, same rule. The -4 increases by 1. We add 1 on there to get t to the -3. And again, we're going to divide by our new exponent. So 1/3 divided by -3 is going to give us 1/9, -1/9. Okay, so our antiderivative of h is that guy. And let's add on the c at the end. I didn't mean to make that t look like it was in the bottom of that fraction. It's -1/9 out front times t to the -3. Okay, so yep, it works for negative exponents. Does it work for polynomials that have more than one term? You betcha. So here's a 3-term polynomial, and we can just take the antiderivative of each individual term separately and add them up at the end. So the integral, the antiderivative of x. Let's see, again, the exponent first. 2 plus 1 is 3, so we have t cubed. Divide by the new exponent, 4/3 out front. Minus, let's see, this was t to the first, so we're going to add 1 to that. So that becomes t squared. So t squared, we're going to divide by the new exponent 2, so that's going to be -1/4 out front. And then remember, this is 8t to the 0. Adding 1, we get t to the first. 8 divided by 1 is just 8, so we end up with 8t. And at the end, our friendly constant. And once again, you can take the derivative of this guy to see if you did it correctly. And I think if you I said do. If you do the derivative of this guy, you are going to see that you indeed get the original function back again. And now finally, a cautionary tale. Because there is one polynomial that the antiderivative power rule isn't going to work for. And here's an example. So rewriting this as 2r to the -1, we try and use the power rule. So the antiderivative of p. Let's see, again, we add 1 to our exponent. So now we have r to the 0. That's not a problem, but you have to divide the coefficient by the new exponent. Uh-oh, we just broke math. 2 divided by 0, undefined. Okay, so in point of fact, the power rule will not work for just 1 over a variable. Okay, we're going to learn the integral of that later. So there you have it. Now it's your time to practice. Students commonly confuse taking the derivative with taking the antiderivative, and they take the derivative when they meant to take the antiderivative. So here's a mnemonic. If you're taking the derivative, the exponent goes down, right? And if you're taking the antiderivative, the exponent goes anti-down. Oh wait, that's up. It's kind of dumb, but maybe it'll help you. See you next time.